In this video, we're going to take a look at complex numbers. Now, to look at complex numbers, we must first start with an imaginary number. So let's do something that we've never been able to do before. The square root of a negative number. Remember, a square root is saying what number times itself gives me the number inside that square root. So what number times itself gives me -1. And we've always said that's impossible because if we take two positives and multiply them together, it's positive. Two negatives multiplied together is also positive. This is where imaginary numbers come in. The square root of negative 1 is defined as I, where I is an imaginary number. Now you might be saying, well, why are we going to bother to study things that don't exist? Now, just because we say imaginary doesn't mean it doesn't exist. It's still very applicable. It's still very necessary. Imaginary numbers occur in a number of places, especially in currents and waves. So if you're thinking about electrical systems, imaginary numbers come into play all the time there. So they're very important. It's just something that we can't necessarily see as easy as we could in other places. So for instance, if we think about a quadratic equation, this is one place the imaginary numbers are going to come up a lot. If we had let's say a rocket ship took off, went up, came back down, it's very easy to see the path of this thing. The two x-intercepts make complete sense. Right here, we can calculate those. That's when the thing's in the ground. What about quadratic that looks like this? There's no x-intercept anymore, but it still has to have the same basic properties. Everything in math has to have the same basic properties. So there must be two roots in this quadratic equation. We're going to start calling our x-intercepts roots because x-intercepts cross through the x-axis. Roots still solve the equation. It's still what solves it when it's set equal to 0. It just might not be passing through the x-axis anymore. So there's still two roots. We can't see them though because it's no longer a real number. Those x-intercepts aren't there. We have imaginary roots, so they still solve the equation. Imaginary numbers are also used oftentimes to make other calculations easier. We're not going to get into that as much in 171, 172. Going to see that a little bit more. So anytime we see a negative inside a square root, if we take square root of -9, the first thing we do when we see that negative is telling me there's an imaginary number, I'll pull that I to the front. So I'm going to have I square root of 9, and then the square root of 9 of course is 3. So square root of -9 is just 3i. Notice we tend to leave the I in front of the square roots, but the i's tend to go behind whole valued numbers that are outside the square root. So if we take the square root of -25, first thing we want to do is pull out the I, then we're going to take the square root of 25, gives us 5i. Now, we can raise these i's to power, so we know that I is equal to the square root of -1. So what if we have an I squared? Well, I squared would be saying take the square root of -1 times the square root of -1. I know anytime I see a square root times itself, it's just a value on the inside. So I squared actually turns into -1. It simplifies. In the same way 2 over 2 simplifies to 1, I squared simplifies to -1. I cubed, that would be equal to square root of -1 times the square root of -1 times the square root of -1. Well, we just saw that square root times itself is -1, so this time we're going to have negative square root of -1. And then square root of -1 is just I. If we have I to the fourth, we're going to have square root times -1 times the square root of -1, 4 times over, you get the point. And I can circle these in pairings. I squared times I squared, notice right there, -1 times -1 is just 1. So I to the fourth is 1. So we could keep doing this, and notice I to the fifth is going to get interesting because I to the fifth is really just I to the fourth times I. Well, we just saw I to the fourth was 1, and I is just I, so 1 times I is I. I to the sixth, well, I to the sixth is really I to the fourth times I squared. I to the fourth just being 1, I squared being the -1 we saw in the second line. So notice what we've done is we've fallen into a cyclical pattern. Imaginary numbers are cyclical, and they have a cycle order of 4. It takes 4 repetitions to get back to where we started. We started with just I, then we went to -1, -I, 1, and then we restart the pattern with I, -1. If we took I to the seventh, that would be equal to -I to the eighth would be equal to 1, and so forth. So that makes it really easy to simplify really large I exponent. So if we had I to the 27, we need to think about how many repetitions in here. How many times have we gone through those patterns of 4? So we could just count it out if we wanted to, or another way we could do it a little more efficient take 27 and divide it by 4, trying to figure out how many times that 4 went into it. More importantly, we're trying to figure out what's left over. So 4 goes into 27 7 whole times, sometimes 6 whole times. If I could do some math, 4 times 6 is 24. When we subtract that, we get a remainder of 3. And so that remainder tells me I'm ending up on I to the third. This is going to be equal to I to the third, and I to the third is just equal to negative I. So I to the 27 is just equal to negative I. You could do this for any exponent. So that's going to help us simplify our imaginary numbers. We always want to simplify imaginary numbers to be either positive 1, negative 1, I, or negative I. We never want to leave I to the third or I to the 27th, anything like that. Let's come back around to this complex number. We've been talking about imaginaries. I still haven't talked about a complex number. Complex number has the form a plus bi. Notice the a has no I attached to it. The a is called the real component. And the b is the imaginary component. And that makes sense because it has the I with it. Now I should note too that if you're ever taking a physics class, you're going to see J's instead of I's. A couple reasons they like to do that. Physics just always, of course, likes to be difficult. Us math people always like to have a nice joking relationship with physics. But also the I is used a lot in current. It stands for current, and current comes current imaginary numbers oftentimes related to eliminate or reduce confusion. They use J's. Also, it makes it nicer when we go to graph these things in a little bit, especially when you get into vectors. So vectors use I's and J's again. We're not going to discuss vectors in this video, but it makes it a little bit easier there. Let's talk about these complex numbers. An example could be 2 plus 3i. So the 2 would be our real component, the 3 would be our imaginary component. Well, if I wanted to take that and add that complex number to another complex number, negative 3 plus 4i. Well, we can think about the i's very similar to how we did with the x's. Similar terms, they're like terms. So the 2 and the negative 3, those are both real components, so I can add those. 2 plus negative 3 is a negative 1. The imaginary components, the 3 and the 4, those are like terms, so 4 plus 3 is 7. So our answer is negative 1 plus 7i. Let's do another one where we make it a little bit more complex. So let's take negative 2 plus 3i minus 1 plus 2i minus 4i. So I have 3 complex numbers. In fact, this last complex number, the negative 4i, has no real component to it. So I'm going to just go through here. I'm going to follow the operations. If I want to distribute, I could, but I just can kind of pick out the like components as I get through. So negative 2 and the 1 are like terms. Negative 2 minus the 1 is a negative 3. And we're going to combine the imaginary portions, the 3, the 2i, and the negative 4. So 3 minus 2i is going to be 1i, minus 4i is going to give us a negative 3i. So our answer, negative 3 minus 3i. Now, if we're going to work with real values, so say we have the square root of negative 27 times the square root of negative 4. We want to be careful whenever we're dealing with square roots of negative numbers. We always want to factor, or we want to pull that I out first. So for the 27, I need to pull my negative out as an I, and 27 stays on the inside. 4, exact same story. I have the 4 that stays on the inside. I pulled my I out, and the reason it's very important to do that, if we multiply roots, we multiply what's underneath. So 27 times 4, we get 108. But we have that I times I, which is an I squared. Notice if we'd started by trying to multiply the negative 27 and the negative 4 in the first step, we would have gotten a positive square root of a positive 108, and that would be false. We always want to pull those negatives out first. And of course that negative, that 108, should still be under the square root. Forgot my square root. Now we should always see if we can pull something out. So 108, if I factor that, try that again, 108. Let me rewrite that. If I take 108 and factor it down to look at what I can pull out, 2 goes into 108 54 times, 2 goes into 54 27 times, 3 goes into 27 9 times, 3 goes into 9 3 times. So that tells me a pair of 2's, a pair of 3's can come to the outside, which is a 6, and I'm left with the square root of 3. Now I squared, I still need to simplify that the same way we were doing earlier in the video. I squared is a negative 1, so we get a negative 6 square root of 3. So let's do another operation with some complex numbers. Let's say we have square root of negative 4 plus 2i minus 3 square root of negative 9i. Negative 9. Don't want the I in there yet. We're going to have to pull that I out. So if we take the square root of negative 4, first thing we said we have to do is pull out the I. Then we're going to have the square root of 4. We'll deal with that in a minute. 2i, not a whole lot I can do with that right now. And then the 9, negative 9, we want to pull that I out. So we're going to have 3 times the I. The 9 still on the inside. Square root of 4 is 2i, plus another 2i from the middle there. And then the square root of 9 is 3, so we're going to have 3 times the 3i because they're sitting next to each other, so they have to be multiplied. So we're going to have a negative 9i there. 2i plus 2i, 4i, minus 9i gives us a negative 5i. Let's do one more thing with these complex numbers. So we can graph complex numbers, but we can't do it in the traditional XY sense because x and y both are real there, and we don't have real numbers. So instead of using x and y, we're going to use a real and an imaginary axis. Like I said, we can't necessarily see these things. We can't see them like the rocket ship taking off. Doesn't mean they don't exist. Doesn't mean we can't still graph them. We just have to graph them in this other imaginary plane. So let's say we had 2 plus 3i. It's the same thing as if we had a point 2, 3 in the real plane. We're going to move to the right by 2. We're going to move up by 3. There would be my point 2 plus 3i. Let's take negative 4 minus I. I'm going to have to move along my real plane, negative 4, because that's my real component. I'm going to move down my imaginary plane by 1, because the negative I, negative 1, understood 1 out front, tells me to move down by 1. So graphing these things, relatively simple. Otherwise, these imaginary numbers behave very similar to any other number. So we already did some addition, we did some subtraction. We could also multiply 2 minus 3i times 1 plus 2i. Can multiply these, just FOIL it out. 2 times 1 is 2, 2 times the 2i is 4i, negative 3i times 1, negative 3i, negative 3i times 2i would be negative 6i squared. Can do some simplification here. 2 plus 4 minus 3 is just a 1 or 1i. And then the I squared, we talked about this before. We never want to leave higher exponents on the i's. We want to simplify it to either 1, negative 1i, or negative I. Well, I squared is a negative 1, so we're going to have negative 1 times that negative 6, which is going to give us a positive 6. So I can add the 2 and the 6, get 8, 8 plus I. So that's maybe the only way it's a little bit different, because typically we would just leave x squared or whatever variable was squared. Here, i's we do want to simplify so that we only have that 2-term complex format. We have our real portion, we have our imaginary portion in 2 different terms.